Good day, class. For this video, I'll be talking about fluid kinematics on a high-level basis only, as it contains concepts and terms used in succeeding lectures. As to what to expect in this lecture, we will start with Langrangian and Eulerian descriptions. Who are they, and what are they for? And discuss what flow patterns are and what kind of flow visualization techniques have been done over the years. Lots of fluid flow data, other kinematic description, and finally, Vorticity, Rotationality, and Reynolds transfer. You can learn more about this in Untitled Chapters 3. So before that, let's define again what is kinematics and what is fluid kinematics. As you recall from general mechanics, kinematics is simply the study of motion. And for fluid kinematics, it's the study of how fluids behave, basically how fluids flow and how to describe fluid motion. We mainly use Langrangian for dynamic rigid bodies, where tracking the individual fluid particles is the game. Again, this is the main proponents are Joseph Louis Lagrange, and then the Eulerian description for the proponent will be Leonard Euler. Actually, it's Eulerian description, and the proponent is Leonard Euler. Leonard Euler. I'm still getting hang on the pronunciation. So again, for the Lagrangian description, the way we describe particles, especially when we are required to tracking the position and velocity of each particle, each individual fluid particle, something we have done before, even in mechanics. We're talking about Lagrangian description. We're talking about the position vector, its velocity at a particular point in time. For Eulerian description, it comes when tracking a particle becomes complicated, when there's too much particles to track. Eulerian description is a better suited way to describe particles, where it uses controlled volume analysis, where at any point XYZ, XYZ components or XYZ position, you know the position and the velocity with respect to time. Actually, both has a time component to it. This looks a bit complicated, but all you need to know about the Lagrangian description and Eulerian description for this particular slide is that these are the variables involved for Lagrangian and Eulerian description. For Lagrangian, fluid particles, aka material particle, you're talking about XYZ position axis with respect to time t. And from here, you will know the local value of velocity field, which contains particular velocity vectors with respect to time and with respect, and the velocity, the resultant velocity vector has its own velocity components x, y, and z with respect to a particular time. The same way with Eulerian description, here we have an acceleration of a fluid particle expressed as a field variable. The acceleration is indeed has a xyz component, and it is the change of velocity with respect to time plus the dot product of velocity vector and del operator here. So where this operation here is the advector correlation. And then, of course, it has its own Cartesian coordinate system plus a plane. And normally you would be using a matrix, something that we won't be doing. Next is material derivative. It is what it is. It is assigned a special motion d with respect to dt in order to emphasize that it is formed by following a fluid part as it moves through the flow field. Okay? So when you apply the material derivative to a specific fluid property, example, velocity, temperature, or concentration, for a fluid particle, it accounts for both changes in that property at a particular location in space and how the particle moves through space. In other words, it accounts for both convective and temporal changes in the property, making it particularly useful for describing the behavior of individual fluid particles as they flow through the fluid. And normally, material derivative is commonly used in Navier-Stokes equations, which describe the motion of viscous fluid flows, as well as other equations of fluid dynamics. It's a crucial concept in understanding the motion of fluid motion and essential applications like fluid dynamics, aerodynamics, and heat transfer. Okay, so this is just a mathematical way of saying, okay, this is how we observe the flow for a given fluid, whether it's water or air or gas, in a particular control setting, and you're gonna time it at from 0 second, 10 second, 15 second, minute seconds. Okay, and sometimes it's you want to know what's happening, the flow against a particular solid object. Say you're trying to determine if the car is aerodynamic, or if your wingspan is able to generate enough lift. So you want to know what the high pressure are, what the low pressures are, but more on that later. So again, these are all very, very high level math. But that is usually if we cannot visualize to get the whole picture. You normally see this sort of visualization like in simulations after numerical calculations to validate findings. And some of them are in the form of streamlines. And these are some of the examples. We have at least 5 here or 6. So for flow patterns and visualization, to visualize what the math is telling us, we have streamlines and streamtubes, path lines and strip lines. And the other two for the following slides are timelines and refractive visualization techniques. So streamlines and streamtubes, as you can see the definitions here, essentially streamline, which you will be encountering more commonly in Bernoulli's equation, since we're going to deal with steady streamline equations there. Is a curve that is everywhere tangent to the instantaneous local velocity. Okay, maybe not the most sexiest definition at all. Okay. A stream tube consists of a bundle of streamlines, much like a communication gate consists of a bundle of fiber optics with one core difference. The streamlines can go outside that boundary of stream tube. The path lines, which is you're probably much more familiar with, is the actual path traveled by an individual fluid particle over some time period. We've used this before in dynamics, and we're going to be using also the same principles in fluid dynamics. So before, we're talking about a guy traveling or car traveling from point A to point B. What's its instantaneous velocity at this particular point in time, and what's its total displacement overall at this point in time. The same way we're doing with the fluid particle here, except for our applications, we'll be dealing with steady flow, incompressible fluids in Bernoulli's equation. Okay. So with streak lines, I think you've seen some simulations just like this before, where this one is a locus fluid particles that have passed sequentially through a prescribed point in the flow. So yeah, so this is something we want to know the effects. Okay, what if there's an object in between trying to interrupt the flow? What is the effect? What is the after it passes the object, what is its nature? What is its behavior? So here you're seeing here it's creating a little bit of mini vortices and rotationality, and you're seeing that somehow it's disrupting particular set of streamlines and not just straight lines as well. Here are other methods of flow pattern recognition and visualization. So here we have timelines, where a set adjacent of fluid particles and that were marked at the same or your instant in time. This is just a graphical representation, but the United States Navy has this particular. I wonder if I could show it. Forgot to just paste it here. Basically, the United States Navy have a lab where they add a dye in one end, and then now integrate the flow, so that now they're not able to understand the wave patterns, and in this case, particularly the flow patterns, what its behavior over a period of time 1, 2, and time 3. The other one is refractive visualization. So we have shadowgraphy and Schlieren imaging, where you get in Schlieren, you get to see involves lenses or mirrors in a image or other cutoff devices to block the refracted light. So when it's really super hot and you get to see some light refraction happening, yeah. So that's what you're observing their vertical camera form. Here naman is a shadowgraphy. An image or a shadowgram produced by the shadowgraph method is formed when the reflected rays of light rearrange the shadow cast into viewing screen or camera, causing bright dark shadows, dark patterns appear in the shadow. You can actually also do this in a pool where you can create a vortex there. And since the vortex kind of refracts light, there will be a dark shadow in between, in the middle of the vortex, because it's refracting light away from the middle. Here are several more. We have profile, vector, and contour plot. Something that you will see in testing vehicles weather prediction, especially in vector plot, from eddies, and checking for significant air resistance, basically, and also in significant design hydrodynamics as well. Okay. Of course, just like our solids, fluids but an experience of deformation of fluid elements. Jovian translation. We have yung rotation. This one translation meaning it just moved from one point to another. Translation, it rotates. Linear strain. And then your shear strain on an angular level. Okay. And we learn a lot about this in basic set during discussing about fluid properties. Remember viscosity, the coefficient of viscosity. Fluids experiencing shear strain, especially at the point of contact, because there's no slip conditions, especially if it's not moving the solid object. Okay. And then we have several properties data like vorticity and rotationality. Essentially what they are related concepts in fluid dynamics and vector calculus, both of which describes yung rotational behavior of fluid or vector field. High vorticity at the point in a fluid flow indicates that the fluid particles at that point are rotating, while low vorticity suggests less rotation. A vector field with a non-zero curl or rotationality represents a system with rotational aspect. In fluid dynamics, it's almost equivalent to vorticity. Okay? So essentially, vorticity describes the local rotation of fluid. And it quantifies the tendency of the fluid elements to rotate about an axis, kind of like a movement, so to speak, but in fluid terms. And then rotationality is a measure of rotational effect or the tendency of the vector field, not limited to fluid flow. It quantifies how much of the vector field behaves like a rotating system. Here is yung Greek symbol niya, vorticity for zeta, and yun sa rate of rotation, the angular velocity. Fortunately, we won't be doing much of that. And here's the derivation that makita nyo is just kind of like there's a cross product here, kind of similar to what you do in statics, and you will yield this particular Cartesian vector rotation. Just to give you another view then, here's the Reynolds transfer theorem, RTT. Essentially, Reynolds transfer theorem is the time rate of change of the property V of the system is equal to the time rate of change of V of the control wheel plus the net flux of V out of the control wheel by mass crossing the control surface. Essentially, Reynolds theorem is a tool that helps you understand how the amount of something like water, heat, or any substance changes in a fluid as it moves through a defined space or defined region into and out of a region. It's a fundamental concept of predicting how things behave in fluid dynamics and other fields of engineering. Essentially, there's a fluid here passing through a controlled volume, and then it goes out the system. So, just to refer what I said, the time rate of change property distance and the time rate of change of P on the controlled volume, so what's happening here, and then the net flux of P, that's basically what this equation is all about. So you start here first, crossing the controlled surface, there's a particular mass of fluid going in. Coming in here, where you change your property in B, and then you will determine the mass crossing to the surface. the relationship between material derivative and Reynolds transfer theorem is that Reynolds transfer theorem for finite volumes integral it's analogous to material derivative for infinitesimal volumes. So here, in Lagrangian description, we convert it to Eulerian description. If we cannot track a singular particle, we convert it to Eulerian description so that we can track it at a controlled volume state and observing all variables at the same time. For Reynolds transfer theorem, which is something you would be noticing that we gotta be doing this Reynolds equation, since we're gonna deal with steady flow for mass flow rate and controlled volume conditions. And here we go from system analysis to controlled volume analysis. Okay, that's pretty much the lecture for fluid kinematics. Thank you.